All right, so this is the analysis lab for doing the pH lab. And so if you really think about it, there are a couple of different kinds of calculations. One is trying to predict the pH of strong acid. So pH of, let's say, 0.01 molar HCl. So we know that HCl is a strong acid, so it basically the concentration of HCl is equal to the concentration of H3O plus. Okay, so if the pH then is equal to minus the log of the H3O plus concentration, in this case it's also equal to minus the log of the HCl concentration, which means it's minus the log of 0.01. So then this is base 10 log, so that would be a pH of 2. Okay, so that would be a strong acid. Now the weak acid is a little bit more difficult. So let's say we have the pH of a weak acid like acetic acid. So if we, you're going to measure the pH, but I think the Ka of acetic acid is 1.8 times 10 to the minus fifth. So this is the theoretical pH. Okay, so we now need to set up our classic sort of ice table. So the ice table would be initial. So we have, in this case, acetic acid. I'm just going to abbreviate that. HOAC is in equilibrium with H plus OAC minus. So we'll start with 0.01 molar. Here, we'll assume the water, though, is 1 times 10 to the minus 7th molar, if we assume it's pure water, and our acetate is 0. So that's our initial. Then we have our change, and our change will lose some here. We'll gain some over here that should be about the same amount. So then at equilibrium, we've got 0.01 molar minus X. We've got 1 times 10 to the minus 7th plus X, and we've got X. Okay. So now if we write the Ka equation, we're going to put H plus and OAC on top. Okay, now if we add maple, and then we know that this is equal to the Ka. Okay, and if we had maple and we really wanted to, shove ourselves around, we could solve this for X, and we wouldn't really have any trouble. I like to take a simpler approach, okay, and we know, generally speaking, that our number is going to be probably way smaller than 0.01 and way bigger than 1 times 10 to the minus 7th. So we can make some assumptions and we can simplify this then to X times X divided by 0.01 equals 1.8 times 10 to the minus 5th. Okay, so if you do that, then it equals 4.3 times 10 to the minus 4th. Okay, so that is definitely way bigger than that and way smaller than that. So our assumption is safe. And so that means then our pH is going to be, since that is equal to the H plus, our pH is going to be minus the log of that, base 10, or 3.37. Okay, so that would be how to solve that for a weak acid. Okay. Now the other question then is, what if we have, after you've done the experiment and you've gotten the pH, how do we get the Ka? Okay, so let's say that we've had a 0.5 molar solution has, let's say, a pH of 2.56. Okay, so the question is calculate the Ka. Okay, so if we do that, then pH is, we need to convert that into H3O plus. So that means that our H3O plus is 10 to the minus 2.56, which equals 2.8 times 10 to the minus third molar. Okay, so if we set up our ice table again, then we've got HA going to H plus or H3O plus A minus. Okay, and so we know our initial then is 0.5, 1 times 10 to the minus 7th, and 0. Our change then will be minus x plus x plus x. Okay, and so then we know, okay, 0.5 minus x. Now what we know here is that we know this one because we know the pH. So this is 2.8 times 10 to the minus 3. Okay. Now this number is way bigger than this number. So we can assume that x equals 2.8 times 10 to the minus 3. Okay. And then this, so that means that this is also 2.8 times 10 to the minus 3. And this number is too small to be affected by that. So we'll just rewrite this then. We'll simplify this as 0.5. If you wanted to, you could say it was 0.04972 if you wanted to, but to be quite honest, it's not worth it. So then the Ka is going to equal these two squared, because they're times each other, divided by this, 0.5. So then that will be 1.6 times 10 to the minus 5th. Okay. So let's say we have a pH of a salt solution. We want to know the pH, or the pK, or the Ka. So let's say we have, ammonium nitrate. And its pH, so 0.1 molar, has a pH of, let's say, 5.7. So the question is, what's the Ka? Okay. And so, so we can dissolve this. Okay, so if we know that this is totally soluble, so it's going to yield an H4 NO3 will yield NH4 plus NO3 minus. Now the question is, which of these can act as an acid or a base? And so what you can see is this compound, this is the conjugate base of a strong acid. So it is a very, very weak base. But this compound is the conjugate acid of ammonia. Okay, so it's conjugate acid of a relatively strong base. Okay. Or medium-sized base, whatever you want to call it. We'll call it a weak base. It's not something that automatically dissociates. So this molecule can dissociate. Okay, we know that ammonium can make an acid, and that would explain then why this thing is a little bit acidic. So now the question is, how do we get the pH then? Okay, now in this case, the nitrate doesn't contribute anything. So if you had something where both were contributing, then they might counteract each other. Okay, so you have to look at the ions and decide which one, if either of those have acid or base properties. And if it's a nitrate, chloride, bromide, any of those, sodium, any of those, they're just not going to contribute. But in this case, ammonium does. Something like acetate would, something like carbonate would. Okay, so now we need to figure out the pKa, or the Ka, sorry, I keep using pKa. So in this case, we know if this is 5.7, we can just take the minus the log of that. In that case, that gives us 2 times 10 to the minus 6 molar. Okay, so now we're kind of in the place where it may have an effect, but let's say we start with in this case, it's 0.1 molar. So 0.1 molar. That doesn't matter. So in this case, 0, and in this case, 1 times 10 to the 7th. So then we're going to subtract x, we're going to add x, and we're going to add x. Okay. Now we know that this one is 2 times 10 to the minus 6th. Okay, because of that. So that means that this. Now the question is, do we, really want to make this, 1.9 times 10 to the minus 6? It's probably not worth it. We can just go ahead and ignore it. Makes our life a little bit. But if you wanted to, you could say, all right, this is, 1.9 times 10 to the minus 6. And then this one, of course, is way smaller, so this is still 0.1. Okay, so then if we set up the Ka, that would equal 2 times 10 to the minus 6 times 1.9 times 10 to the minus 6 divided by 0.1. Okay, so if you do that math, you get 3.8 times 10 to the minus 11. So it's a pretty weak acid. Okay, but it's still an acid and still makes it a little bit acidic. Okay, so that would be the trick on how to do all the types of calculations for this lab. You're obviously going to have different numbers, but the setup is always the same. If you have any questions, please be sure to come and see me.